least understood mysteries of the universe are objects which appear to be just a tiny fraction of the size of a typical galaxy. And yet, they emit the equivalent energy of 1,000 Milky Way galaxies.
In the 1920s, Edwin Hubble was transforming our vision of the universe with discoveries he was making with the 100-inch telescope at Mount Wilson. And even as he was making these new discoveries there, this telescope, the 200-inch telescope on Palomar Mountain, was in the planning stages, was underway. And Hubble, with the 100-inch telescope, of course had discovered that there were galaxies out beyond our own, had proved that, and had also shown that these galaxies were moving away from us, that in fact the whole universe was expanding. But in its way, this telescope here proved that the universe was even stranger than Hubble found it to be. In fact, it brought us puzzling details that made the universe just seem curiouser and curiouser. An important part of those new discoveries of the 200-inch telescope was the quasi-stellar object. Now, quasi-stellar objects were first found as radio sources, and eventually it became possible to pinpoint the positions closely enough with the new radio telescopes so that we could look with telescopes like these to see what was really there, giving off the radio light. And it turned out that there was an entire universe of strange objects that became visible to us. Now, some of radio sources turned out to be peculiar galaxies, actually. They were emitting, however, huge quantities of rather exotic forms of energy, infrared, for example. Others of these new objects just appeared in the telescope to be stars. These then became known as the quasi-stellar, or sort of stellar, radio sources. And actually they were rather unassuming, star-like objects, fairly unimpressive really. And they remained unimpressive until Dr. Martin Schmidt took spectra of at least one of them and identified hydrogen lines in the spectrum of the quasar known as 3C273.
Astronomers can determine the speed at which a distant object is traveling toward or away from us by measuring the red shift in its spectrum. Light travels in waves, and in the visible region, the shorter waves appear blue and the longer waves appear red. If a star or galaxy were moving toward us, its light waves would crowd together and appear to be blue. But if an object like a quasar is moving away from us, its light waves are stretched out and appear to be shifted to the red end of the spectrum. The phenomenon is called the Doppler effect, or, in this case, a red shift.
Martin Schmidt realized that this red shift was due to the Doppler shift. At least that's what he thought. The Doppler shift of the galaxy, or in this case, the quasar, the quasi-stellar radio source, moving outward from us, and in fact at an astounding speed, 16% of the speed of light. And even more astounding, another one of these quasars had a redshift that corresponded to 37% of the speed of light. Well, Martin Schmidt concluded that the universe was expanding, of course, and that the quasars were taking part in this just as we had known the galaxies were doing before. The quasars then were interpreted as very distant objects, and because when we look very far out into space, we also look far back into time, the quasars gave us an earlier look, a look at the youth of our universe. Well, since that time, the debate over the identity of the quasars has simply continued, and it's reminiscent in a way of the old arguments of the true nature of galaxies, whether they were close inside our own galaxy or out beyond it. And now we know, of course, that the latter is the case. Well, quasars are thought perhaps to be very distant and energetic objects, or, alternatively, closer objects, but very strange, bizarre objects that perhaps obey a physics all of their own. This Pandora's box of possibilities was all opened in 1963 when Martin Schmidt succeed in obtaining and interpreting the first spectrum of a quasar.
It came as an inspiration, essentially. There were in total 5 or 6 lines in the spectrum of 3C273. And one afternoon, when I was sitting at a desk writing a manuscript about the observations, I realized that among those 6 lines, if I forgot about 2, that the others seemed to be regular in spacing and in intensity. For some reason, I started to make an energy level diagram on the basis of what I saw. I made a mistake in the arithmetic. I became slightly irritated and said to myself, but there is regularity there. In order to check that, I took the ratio of each of the lines I had under consideration to the Balmer lines of hydrogen, which after all are very regular. Well, in the first case, the ratio came out to be 1.16. The second ratio, 1.16. Third ratio, 1.16. And suddenly it dawned upon me that this was a redshift of the Balmer spectrum itself. That was a shock. I sat there for perhaps 5 minutes checking things, and it appeared to be it. And I started walking around the office and into the hallway, and I met Jesse Greenstein, and we went over it together. And within about half an hour, after he had pulled out his observations of an earlier radio star, quasar 3C48, we found that we could also explain its spectrum with an even bigger redshift of 37% or so. That was a shocking experience, and I remember that night again pacing around at the house and thinking of all the consequences for the future, because it was clear that if such a bright star had such a big redshift, that very faint such objects should have much bigger redshifts. And the prospect of, with these objects, seeing almost all through the universe was mind-boggling.
As exciting as quasars are, it soon became apparent that they presented us with a real dilemma to our understanding. Now, some of them are radio sources and some of them aren't, but in any case, they do show tremendous redshifts. And if we interpret these redshifts as due to the Doppler effect, this must mean that the quasi-stellar objects are going away from us, receding faster than anything else that we know in the universe. Well, the quasars obviously must be beyond our own galaxy. For one thing, we don't see any motion across our line of sight, and therefore they've got to be farther away than the distance across our galaxy. So if the quasars are at cosmological distances, the distances that their redshifts indicate, then we must be seeing them at, say, 10 billion light years away from us. Well, this is incredibly far away, and so these objects must be incredibly bright to still see them at that great distance. They must be, in fact, hundreds of times more luminous than ordinary galaxies. Well, how do we explain such a thing? Perhaps the quasars are simply supergiant galaxies, but this explanation really doesn't work. We know that the quasars vary in brightness over a period of a few weeks or months, and a huge object cannot change that quickly, that much in its light output. The energy, then, in a quasar must be coming from a region just a few light weeks or light months across. And yet the quasar is shining with the light of 1,000 Milky Way galaxies, the equivalent of 100 trillion stars. And yet, this light is coming from a volume whose diameter is no greater, perhaps, than 100th the distance from here to the nearest star. So a quasar, then, is really just a lot of energy coming from a very small place, and explaining the source of that energy simply isn't easy. Well, people have tried to get around this by proposing alternate explanations, proposing, in fact, that the quasars are really closer than their redshifts indicate. But if they are closer, why do they have such huge redshifts? Well, some of the people grappling with this problem have proposed very exotic, and unorthodox explanations for the quasars and their redshifts.
The redshift of quasars is now generally believed to be cosmological, but especially in the early days, about 15 years ago, many other explanations were considered. One was that the redshifts were due to the explosion of a fairly local object. In fact, Terrell at Los Alamos proposed that it was perhaps an explosion from our own galaxy. And therefore these objects would be relatively nearby, and they would not be so intrinsically bright and be more modest objects. Another explanation that came up very soon, and that Jesse Greenstein and I discussed extensively, was the possibility of gravitational redshifts. The redshift that is caused because the photon has to escape from the object from which it is emitted, have to overcome the gravitational potential difference to us, and it loses energy and therefore is redshifted. In both of these cases, there were, I think, compelling arguments soon produced why they were untenable. And therefore, strangely enough, the best remaining competing hypothesis, competing that is with the cosmological nature of the redshift, the best competing hypothesis is, strangely enough, one that says we don't know. Unknown, but not cosmological. And this, as you know, is advocated by Dr. Aap, Dr. Burbidge, and Dr. Hoyle.
In 1966, I noticed that the quasars tended to be closer to large galaxies than you would expect of randomly oriented objects. And following that clue up over the years, I have found more and more evidence that the quasars are closer to galaxies, and they're particularly closer and associated with disturbed galaxies that look to be explosive in nature. And I have concluded that the quasars actually associated with these galaxies and are ejected from the galaxies, and therefore are at distances much closer than their redshifts indicate, and that therefore the redshifts of the quasars are due to some other effect on Doppler expansion, some unknown redshift mechanism. One example of an association of quasars and galaxies was discovered by me in 1970, and I was just studying the distribution of quasars on the sky, and I noticed a particularly tight group of quasars. And if you look at a diagram of the sky, you'll see these four quasars very close together. And if you look more closely, and you will see that these four quasars form a very straight line. Moreover, the quasars in this line, for the most part, tend to resemble each other quite a bit. They have very much the same redshift, the same radio properties, and so forth. So they seem to be, the same kind of quasars seem to be related to each other. And if you follow this very straight line which they form, it goes back into an exploding galaxy. And if you look at the photograph of this exploding galaxy, you see that it's really disrupted, and that the line of quasars leads right out from the center of this galaxy, which leads me to conclude that the explosion which disturbed the galaxy is the cause or the result or connected with the ejection of these quasars.
I would say that I don't feel at all certain just where in the history of galaxy does the quasar phenomenon come. The fact that the matter, we're sure that the matter is in a very dense state in part of a quasar, and that's a consequence of gravitational collapse. So if one thinks of the quasar as an early stage in galaxy formation, one has to think of ways of getting the material out from such a compressed state out to form a galaxy as we know it, like our own Milky Way. On the other hand, if they are at cosmological distances, then they seem to be more numerous in the past at large distances. So one would have to either call them the dying stages of a previous generation of galaxies, perhaps an early primordial type of galaxy or the beginning stages of galaxies as we know them today. That's if they're at cosmological distances. Let's take the usual assumption that the quasars are at cosmological distances. If material formed somehow in the early stages of the universe then into gobs of matter which are going to contract and form stars and be the galaxies that we know them, supposing an amount of material of this sort did not contract in that usual way, or in which there was time at some stage for formation of stars, suppose it just had too little angular momentum or something like that, collapsed into one big lump of material. That could be an alternate way of evolution of amount of material that we are used to seeing in galaxies.
Quasars may be associated with peculiar galaxies, but the evidence for this is largely statistical, and therefore it's subject to a wide variety of interpretations. And we've got to ask ourselves then, are these associations coincidence or are they real effects? And it's hard to know where to draw the line. And still, we have to explain the redshifts, that they're so large. Now, the history of science has shown us that it's usually the simplest idea, the idea for which there is still experimental evidence and theoretical support, that gives us the best chance of coming out right. Sometimes the unconventional does lead us to a new understanding, but usually it's that simple and logical step that leads us forward. And with the quasi-stellar objects in the last 2 decades, the evidence has been mounting that these redshifts that they show us are cosmological, that is, due to the expansion of the universe. This means that the quasars are very far away, and this is the view most astronomers adopt today.
The nature of quasars remains, of course, very uncertain. We see similarities between nuclei of galaxies and quasars that are quite remarkable in terms of variability, infrared emission, high motions, large velocities, and so on. And it seems attractive to think that the nucleus of a galaxy is really a mini quasar. And that then would perhaps suggest, but this is really speculation, that quasars are the birth stage of galaxies, or at least of their nucleus. So that when a galaxy is born, it starts with a nucleus that is super bright. We call it a quasar. We don't see the galaxy because the nucleus overpowers, is so bright. And gradually, this calms down to where a galaxy starts its normal life. That would then also explain why there were so many quasars at very early times in the universe, because most galaxies were born at that time.
Astrophysicists always like to be able to produce an evolutionary connection between various types of phenomena. And many of us at this time feel that there may be an evolutionary connection between quasi-stellar objects, or quasars, Seyfert galaxies, and normal type of galaxies. Simply because if we take a galaxy such as ours, which is a spiral galaxy, and look at a Seyfert nucleus, we find that generally a Seyfert galaxy has an outer region very much like our own galaxy and a very bright nucleus which is producing a lot of energy. If we go to objects which are perhaps even more distant, the quasars, then we find that we're only left with a very small nucleus in many cases. But we feel that the amount of mass involved must be on the order of a galactic order of mass. So it would be very intriguing to postulate, and many people have, that at very early stages of galaxy formation, most galaxies would look like a quasi-stellar object. A very bright nucleus, even more compact than the Seyfert nucleus, with a size maybe only a light year or a light month across, where most of the energy is being produced. Then, as the galaxy would get older, the region of energy formation would expand and become maybe 10 or 20 light years across, and we would see the galaxy as a Seyfert galaxy. And then after all the energy production had ceased in the nuclei of the galaxy, it would look very much like our own galaxy. This is, of course, very speculative, and we do not have direct evidence at this time that this may occur, but it's always something very interesting to think about.
In order to explain how the compact nuclei of galaxies could generate the tremendous quantities of energy associated with quasars, some astronomers have begun to consider concepts such as supermassive black holes. These incredible objects might explain unusual high-energy events occurring in some quasars and peculiar galaxies, such as M87.
Well, I think one doesn't want to overstate the case. That is, to make the claim that we found the black hole, because, well, because we haven't, and because it's so extremely important in astronomy, the whole concept of finding very massive black holes. What has been found briefly is that in the center of M87, in the very inner nuclear regions, there exists a quite large mass, some 5 billion solar masses, which is not composed of the normal kinds of stars that make up the rest of the galaxy. It's matter which is very dark in particular compared to those stars. There is not enough mass in visible stars, that is, the visible stars by themselves do not provide enough mass to hold themselves in at the center of the galaxy. There must be some thing or things other exactly in the center of the galaxy that are not normal stars that are holding the stars there, keeping the galaxy from flying apart at the center. And furthermore, that mass, as I mentioned before, is dark mass. That is to say, only something like 10% of the light, only something like 10% of the mass of this 5 billion solar masses which exists in the center of the galaxy comes from visible stars. The other comes from something which is darker than the normal stars that one sees in all the rest of this galaxy and in similar galaxies, including normal galaxies in the center.
The existence of a supermassive black hole at the center of M87 might help explain the strange luminous jet which stretches 5,000 light years from the galaxy's nucleus. The jet could be caused by electrons spiraling along the magnetic fields of a supermassive black hole.
The indications are very strong that, in fact, it's something in the center that's driving all the anomalous processes in M87. But the details of how one produces a jet, I think, are still not well understood. In fact, I think they're very poorly understood at the present time. The attractiveness of a black hole, from a more general point of view, is that it provides an extremely efficient mechanism for producing large quantities of energy in very small volumes. And that has wide applicability in various aspects of extragalactic astronomy. The most obvious case is that of quasars, which have exactly that property.
Roger Blandford, who is a faculty member here at Caltech, has given recently what is now widely regarded as the best explanation for the power sources of quasars and of outpourings of energy in the form of radio waves from nuclei of galaxies. The idea is this, that you have a supermassive black hole weighing, say, 1 billion times what the sun weighs in the center of a galaxy. You have gas that is sinking near this black hole under the gravitational pull of the black hole and sinks in and then goes whirling around in orbit around the black hole in a large accretion disk, a disk of gas like a thin pancake. Embedded in this disk of gas there is a magnetic field, and these magnetic field lines stick out of the disk of gas in the same way as magnetic field lines stick out of the north and south poles of the Earth and go around. Now, the rotation of the black hole and also the motion of this gas in the disk around the black hole causes the magnetic field there to produce an electric field. And it's a combination of the orbital motion of the gas in the disk and the rotation of the black hole that does this. The electric field then accelerates charged particles, pulls them, accelerates them to high velocities along the magnetic field lines, and they go shooting out of the north and the south poles above and below the disk out to large distances where they hit other magnetic fields and go gyrating around and produce strong radio waves. In this process, it turns out, if your black hole is rotating, basically the power you're getting out in strong radio waves, if you trace it back in, it's ultimately coming from the rotation of the black hole. We don't know whether that theory is correct or not, but it's the best theory we have around at the present time.
When rotation is taken into account, the structure of a black hole changes. A static or stationary limit is formed outside the event horizon. Between these imaginary boundaries is a peculiar region, the ergosphere, where it's impossible for anything to remain at rest, because the space-time itself is being dragged around the hole as it spins. If something fell into the ergosphere at just the right angle and were to break in two, with one piece disappearing forever within the event horizon, the other piece could be ejected from the black hole with far greater energy than that with which it entered. This energy comes from the rotation of the hole, which is now spinning a little more slowly. So it's possible to imagine using a black hole as a massive power generator.
Quasi-stellar objects are probably the relics of the turbulent and chaotic, violent period of the universe's beginning. And we see them as they were then, not as they are. We presume that they have evolved into something else today, probably just ordinary galaxies. And we still don't know the source of the energy that allowed them to shine so brightly when they were young. We might speculate that it was supernovae explosions of tremendously massive stars and galaxies' cores. These eventually produced black holes and neutron stars. Perhaps that's the explanation of the bright quasars. Or maybe instead there's a huge, single, super gigantic neutron star or black hole there. Or maybe something we simply haven't thought of yet. But like a good mystery, the clues to the early universe are there in the quasars. We just don't know how to read them yet. But we're going to continue to collect those clues until we can read them with the world's largest telescopes.